This is section 9.1a, sequences and series. A sequence is a function whose domain is the set of positive integers and sometimes zero. That means that most of the time the domain is positive. Sometimes you can have zero in the domain of these functions, but you will never have negative numbers. Sequences are basically a set of numbers, like a list of terms. And it'll become more clear what they are when you see examples. Sequences may be finite or infinite. And sequences are usually written in the form in which functions are written. f1 or f of 1 equals a1, meaning the first term. F of 2 equals a2, or the second term. F of 3 equals a3, or the third term, etc. These are called terms, and a1 is the first term and an is the last term or the specified term. Again, this will become clear with the examples, but I'm starting with this just so that you get used to how sequences are written. Let's look at an actual sequence. The first three terms of the sequence an equals 4n minus 7 are a sub 1 equals 4 times 1 minus 7 equals negative 3. Notice that what we plugged in for n is just the particular number of term that we were talking about. So a sub 1, the first term, means that n equals 1, so I plug 1 in for n. 4 times 1 minus 7 equals negative 3. A sub 2, it's given that subscript because it refers to the second term of the sequence. And so I plug in 2 for n, and I get 4 times 2 minus 7. That equals 1, because 8 minus 7 equals 1. A sub 3 refers to the third term of the sequence. And so I plug in 3 for n and get 4 times 3 minus 7 equals 5. And so for this particular finite sequence, the first three terms are negative 3, 1, and 5. The first four terms of the sequence an equals 3 plus negative 1 to the n are. Alright, now I would like you to pause the video, try to do this on your own, because doing it on your own will help you to learn how sequences work. Just keep in mind that the subscript n refers to what numbered term you're talking about. So for the first term, n is 1. For the second term, n is 2. For the third term, n is 3. And for the fourth term, n is 4. So pause and then resume when you have an answer for the first four terms of this sequence. You should have gotten 2, 4, 2, 4. And you can get that simply by plugging in the right numbers for n. So for the first term, if n is 1, then I'm going to put 1 in for n here. Well, negative 1 to the 1 power, it's negative 1. And 3 plus negative 1, which is 3 minus 1, that equals 2. Now let's plug in 2 for n. So if I plug in 2 for n, well, negative 1 squared is 1, and 3 plus 1 is 4, and that's why I get 4 when n is 2. If n is 3, that is for the third term, well, then I'm going to put 3 in for n. And when I put 3 in for n, I find that negative 1 cubed is negative 1, so 3 minus 1 is 2, and so on. So you can see how when n is 1, the value of the term is 2, the first term. When n is 2, that is for the second term, the value is 4. When n is 3, for the third term, the value is 2. And when n is 4 for the fourth term, the value is 4. So hopefully you can see how sequences work. They basically act like functions, but what makes them different, or what makes them a subset of functions, is the fact that they're domains are always integers. You're not going to have fractional domains in a sequence, or decimals, or pi or anything. You're just going to have simple integers going in as part of your domain in sequences. And also the thing to remember about sequences is that the domain refers to which number of term you're talking about. First term, second term, third term, etc. The first four terms of the sequence a sub n equals -1 to the n over 2n minus 1 are, and again, keeping in mind that the number n, or the value of n, refers to which number term you're talking about, you should pause the video and do the first four terms on your own. Then resume when you have them. And the answer is -1, 1/3, -1/5, 1/7. So for the first term, I plug in 1 for n, and I evaluate. Well, -1 to the 1 is -1. Plug in 1 for n here, I get 2. I get 2 times 1, and 2 minus 1 is 1. So -1 divided by 1 is -1. If I am now looking at the second term, well, for the second term, n is 2, and so I have 2 going in for n, and -1 squared is going to be +1, and then when I put 2 in the denominator, 2 times 2 is 4, minus 1 is 3, so 1 over 3 is going to be 1/3, and so on. So hopefully you get the point that n refers to what number term we're talking about. First term, second term, third term, fourth term. And the reason I'm repeating that so much is because it's amazing how students do get confused with what n means. But when you just think of it as a count, as first being 1, second being 2, third being 3, if you think of it as a count, then it becomes a little easier to remember. The first four terms of a sequence are 1, 3, 5, 7. What is a sequence? Okay, well, these kinds of problems are probably what students find most difficult in sequences. It's when you have to work backwards. All right, the first two examples here at the top of the screen. For those two, you really are just plugging in numbers. But when you have to work backwards, when you're given what the terms are and have to find out or figure out what the function is, what that particular sequence is, that's where it can get a little tricky, because you have to be able to find the pattern. And there's really no great shortcut for finding patterns. There isn't some kind of formula you can use. You just have to observe and think and try to figure it out. So it's probably why students sometimes struggle with these problems. The best way to handle them is just take it slow, one step at a time, and then you can't go wrong. All right, so the first four terms of a sequence are 1, 3, 5, 7. What is the sequence? Well, let's start by asking ourselves a question. What should I do to each n in order to get the desired term? Okay, and to illustrate that, let me show you this table. Okay, so I know that my domain for this particular function, which I'm trying to find, I know that it's going to be integers. And when it's not otherwise specified, you can really just assume that it's positive integers. All right, so I know that I'm going to have a first term, a second term, a third term, and a fourth term. That's what the problem asked me for. And so the first term corresponds to n equals 1. The second term corresponds to n equals 2. The third term corresponds to n equals 3. And the fourth term to n equals 4. Now on the right side of the table, on this right-hand column, I have what the actual value of each term is. Okay, so don't get confused, as sometimes students do, between the value of the term and its actual number. Okay, just because something is for the first term doesn't mean that its value is 1. In this case it is, not always. Like here, for example, the second term has a value of 3. The third term has a value of 5. The fourth term has a value of 7. So the value of the term is not the same as the number of the term. Okay, the number of the term, the n, simply indicates the order in which that term appears, whether it's first, second, third, fourth, fifth, etc. The value of the term is what the number actually equals. And those values, 1, 3, 5, 7, are given to us. So back to our question, all right, the question, what should I do to each n in order to get the desired term? This is where you have to look at it and try to figure it out. And again, there's no real shortcut for this. It's really just a matter of observing, noticing, and then trying to do things one step at a time. All right, let's look at this first term. If n equals 1 and the value of the term is 1, well, I obviously I don't have to do anything to this 1 in order to get 1. It's the same number. Okay, so that doesn't help me, but let's look at the other terms. Here I notice that n equals 2 and the value of the term is 3. Well, what did I have to do to 2 to get 3? Well, if I'm just looking at how things appear, it seems that I only had to add 1 to 2 and I got 3. But I can't conclude that all I need to do is add 1 to each number, because see, that pattern does not work here. 3 plus 1 does not equal 5. And it doesn't work here. 4 plus 1 does not equal 7. So that can't be it. Let's look at the next term. Well, what do I have to do to 3 to get 5? Well, I could say I need to add 2, but then again, I'm in the same boat. That would not work for the second term nor for the fourth. So it can't be just adding 2. Now, maybe it's multiplying. All right, let's see. What happens if I multiply 3 by 2? I get 6. But 6 is 1 more than 5. All right, so I don't know for sure whether that works, but maybe we're on to something. So what you need to do is you have to test your hypothesis on the other terms. All right, so right now I said for this particular row, third term, which is 5, I said, well, I multiplied the 3 by 2 to get 6, and I subtracted 1 to get 5. Does that pattern work for the other terms? Let's try them one by one. All right, let's look at the first term where n equals 1. If n equals 1 and I multiply that by 2, I get 2. Minus 1 is 1. Okay, so it works there. If n equals 2 and I multiply that by 2, I get 4. 4 minus 1 is 3. It works there. I already know that it works here. 2 times 3 is 6, minus 1 is 5. And now I have to see if it works for the fourth term. 2 times 4 is 8, minus 1 is 7. And therefore I can conclude that this pattern of multiplying by 2 and then subtracting 1, that works. Therefore, my sequence can be written as a sub n equals 2n minus 1. And for that particular sequence, the first 4 terms are 1, 3, 5, 7. So hopefully you see how we do these kind of problems when we need to work backwards. Go step by step, set up your table. Don't get confused between number of the term and value of the term. And then you can find a pattern. Let's look at another example. The first 4 terms of a sequence are 2, negative 5, 10, negative 17. What is the sequence? All right, obviously looking at this, we have something a little more complicated. But again, as always in math, the best thing is to just go step by step. So we're going to ask ourselves the same question. What should I do to each n in order to get the desired term? Still asking myself the same question. And I can also set up a table as I did in the last example. The reason the table is good is because it does give you a visual reminder that the number of n is not the same as the value of the term. All right, the number of the term, which is n, is not the same as the value, which is not going to be equal to n necessarily. All right, so here I have n 1, 2, 3, 4 because I'm asked for the first 4 terms. So n equals 1, first term, n equals 2, second term, n equals 3, third term, n equals 4, fourth term. Now the values are also given to me: 2, -5, 10, -17. And you're going to notice that there's, besides what's going on with the values of the numbers, there's also a sign change. The sign seems to be alternating: positive, negative, positive, negative. So how are we going to break this up into steps? Well, first we're going to attack the sign change part of the problem, and then we're going to worry about the numbers. Okay, if you try to kind of do both things at once, sometimes you can just clutter your mind and get confused and frustrated and all that nasty stuff. So let's just be calm and do it one step at a time. All right, first let's identify what causes the sign change. Why does it go positive, negative, positive, negative? All right, for these alternating signs, it helps to recall, exponents, things you learned in Algebra 1 and 2. For example, look at these numbers. -1 to the 1 power is -1. -1 to the third power, or cubed, is -1. -1 squared is 1. -1 to the fourth is 1. Well, what can we conclude from those 4 examples? We can conclude that if I raise -1 to an odd exponent, I get -1. If I raise -1 to an even exponent, I'm going to get 1. All right, so how can we work that into this problem? I'm going to walk you through the sign change part of it, and then when we get to the other part of this problem, you are going to be on your own. Okay, so let's suppose that my sequence is an equals -1 to the n. Okay, remember that we're only working on the sign change part of this sequence, and we're not worrying about the numbers yet. Okay, that's how we're doing this step by step. So obviously a sub n equals -1 to n isn't going to give you the final answer, but it might help you to get to the cause of the alternating sign. So -1 to the n, if I plug in n equals 1, n equals 2, 3, 4, if I plug those in successively, then I can see that the first 4 terms would be -1, 1, -1, 1. Okay, because if I plug in 1 for n, well, -1 to the 1 is -1. If I plug in 2 for n, -1 squared is 1. 3 for n, -1 cubed is -1. 4 for n, -1 to the fourth is +1. All right, so the good news is I've got alternating signs. But the bad news is it's not the pattern that I need. Okay, so here I have negative, positive, negative, positive. But if I look over here, I've got positive, negative, positive, negative. So what am I going to do about that? All right, this is just a little bit of a challenge because it helps you to learn how to think. Pause and try to figure that out on your own. If you get stuck or if you're clueless about it, well, then don't waste time. But if you like a challenge and you want to figure out what to do to n in order to get the right kind of alternating signs, then pause and try to do that on your own and then resume. So you may have figured this out on your own. If you do a sub n equals -1 to the n plus 1, that would give you the first 4 terms: 1, -1, 1, -1. And I can see that that's much better, right? Positive, negative, positive, negative. And the desired sequence: positive, negative, positive, negative. All right, and all we did was we simply added 1 to n. And that allowed us to get the right kind of pattern in the signs. Okay, so let's walk through it. If n is 1, which means the first term, well, 1 plus 1 is 2, -1 squared is 1. What if n is 2? That is, if n is 2, I'm dealing with the second term, so n is 2. Plugging 2 in for n gives me 2 plus 1. Negative 1 cubed is negative 1, and so I get negative 1 for my second term. If n is 3, and I'm looking at my third term here, well then I plug in 3 for n, and then I get 3 plus 1 is 4, negative 1 to the fourth, and that would give me positive 1. And finally, for 4, the fourth term, when n is 4, plugging in 4 for n gives me 4 plus 1 is 5, negative 1 to the fifth is negative 1. Alright, so we can see how to account for the sign change in this particular problem. Now what we have to do, now that we have accounted for the sign change, we need to worry about the integers and see like what kind of pattern is going on there. So now, ignoring the sign change, let's find a pattern for the integers. Let's find a pattern for the integers. Again, this is a good challenge for you. It forces you to think. So look for a pattern. It's not easy. So for some people it is, but you know, for a lot of people it's not that easy to find patterns. It takes some practice. So again, don't spend hours on this. Don't get stuck, but do try to look for a pattern. Pause now, look for the pattern, then resume after a couple of minutes of trying. Okay, well, this is the final answer, and you might ask, well, how on earth did you come up with that? And see, that's why this is kind of frustrating in the beginning, is because yeah, it makes sense when it's all laid out in front of you, but the question is, well, how did you come up with that n squared plus 1 there? Well, let's look at this final answer, and then since this is the first time that we're doing an example like this, hopefully looking at it, breaking it up, will kind of give you clues for future problems. All right, well, this part, see where the cursor is circling. Well, that part there, we already worked through step by step. Negative 1 to the n plus 1 is going to give us that alternating sign change. Positive, negative, positive, negative. Okay, well, that negative 1 or 1 times anything else is only going to affect the sign. 1 times anything is positive of that thing. 100 times 1 is just 100. And 100 times negative 1 is negative 100. So this multiplied by whatever follows counts for the sign change. All right, and now how do we get this n squared plus 1? Well, again, it's looking at patterns. All right, it's looking at patterns. And if I plug in the different n's, okay, if I look here, for example, and I say, all right, this n is 1 in the table, and how do I go from 1 to 2? Well, just looking at that term, it appears that I'm either timesing it by 2 or adding 1. Well, that doesn't work here. Timesing it by 2 would give you 4, adding 1 would give you 3. So obviously that is off. Okay, and again, remember, I'm ignoring the sign change for now because I've already taken care of the sign change. And since we're doing this in 2 phases, right now I only want to account for the pattern of 2, 5, 10, 17. All right, well, multiplying isn't going to work. Adding is not going to work. Then we can try squaring. Okay, and that's how I come up with this 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16. If we look at this pattern 1, 4, 9, 16, I can see that the way that these numbers vary from the absolute value of this right-hand column of the table is just the square plus 1. Okay, so 1 squared is 1, plus 1 is 2. 2 squared is 4, plus 1 is 5. And remember, I'm ignoring the sign change. That's why I'm not saying negative 5. We're just focusing on the numbers. Okay, 3 squared equals 9. 9 plus 1, 10. 4 squared equals 16. 16 plus 1, 17. So this n squared plus 1 quantity, would account for the pattern of the values of 2, 5, 10, 17. 2, 5, 10, 17. This quantity of negative 1 to the n plus 1 accounts for the alternating sign. Positive, negative, positive, negative. And when I put them all together, when I put both of these together, I get these first four terms, 2, negative 5, 10, negative 17. Okay, again, I've walked you through this example. It's not exactly an easy problem. Again, some people find this easy and fun. Some people find it difficult. But no matter how you find it, taking a systematic approach is always the best way. All right, and also you get better at these with practice. Here's the classwork. Page 649, numbers 9, 17, 23, 31, 39, 41, 42, and 43. And we'll see you in class.